Hello everybody, I'm Nikzad MOTAMEDI and so glad to be here for presenting my works during my tests. I'm professor, associate professor in EMTL Build 2A, and we are going to talk about analysis the surface during the contact mechanism using deep learning for breaking application. So why the contact problem is important? Because for any vehicle like automobiles, trains, airplanes, we have the aspects of safety, also the aspects of the user experience, also the reliability of the system. So for having a better user experience, we need to increase our performance during the contact process. Also, reduce the noise pollution because it's a problem in our society. So for solving this problem, we need to analyze that from different aspects like multi-scale and multi-physical modeling for having a good point of view for analyzing this problem. As the contact problem is a tribology problem, so we are consider and we are look at this part of the science. At first, the tribology is a study of the friction, noise, wear, and also the lubrication when two bodies are in contact. But when we are two bodies in contact, the surface is not so plain. So we have the localization of the contact during the process. And this localization and concentration of the contact induce the heat and the concentration of the stress. This problem can induce the noise pollution. That is the problem in our train station during the braking of the trains. So we need to understand this problem for reducing this noise pollution. Another aspect is particle emission during the contact. This particle emission can have an impact on our water, all of the environment. So understanding this problem is crucial. For understanding this problem, we have some aspects like numerical method, finite element methods, with the complex model like for example, here we have a complex numerical model and or a simplified model, but always we have a gap between experimental modeling or numerical modeling. So we have some scientists that use a complex model or simplified model also in experimental modeling, but always because of the complexity of the problem, we didn't have enough results. For this reason, we are going to use AI. But in this problematic, in this problem, as it's a tribological concept, we are going to look at this problem from three aspects. The first one is the surface are not planned and they induce the noise. The interaction between the bodies, the temperature evolution during the contact, and the last one is the wear. So the first one, as I said, it can be about the surface not plane and the noise during the contact process. So another problem that we have in mechanical aspect is the data. Which data is relevant to our application? Another, the algorithm. Sometimes we have the problem in 2D, like images. So we need to find a good application, good architecture for having a good performance in our AI or deep learning model. Another aspect is the interpretation, because this interpretation can help us to find the relationship between the input and output for having more understanding about the process. This understanding can help us for reducing the process of the learning or training during the training system of our deep learning model. For the first aspect, we are going to have follow this scenario. At first, we are going to generate some surface using the simplified model finite element model to create a database. After that, to find a good architecture, and then at last to interpret our data. As I said, one of the problems that we have for using deep learning in mechanical aspect, we need to have a relevant data. And having data for mechanical model is not so simple. For this reason, we needed to generate data using the finite element method. Here we have a simplified model, and we have just a pin on disk, and the disk is going to rotation. And for each test, you are going to generate another type of surface. As we can see here, if our surface is so plane, the concentration of the stress is there. As we have a surface with another type of geometry, the concentration of the stress is not homogeneous, and it's not in the interest of the surface. For generating our data set, as I said, for each application, we have another surface, and the surface is going to our model. Then, if we have the vibration or non-stability of our system, we are going to create a data set, like a binary data set, for having a surface with the risk of vibration or without the risk of the vibration. One of the problems that we had with this problem, it was the imbalance data set. So we needed to generate enough data for reducing this part, because if we have not enough data for such a problem imbalance data set, we are going to have the risk of the underfitting. For the first application, we used a convolutional neural network, and for the training process, for each surface, we have two labels, non-SQL or SQL. So our algorithm is going to find a correlation between the surface geometry and the risk of the vibration. Here we have some results about this application. Here we have the ROC curves. The ROC curves help us to have a good understanding about the performance of our model during the training and during the testing phase. If our ROC curve is diagonal, so it means that the model is not able to do this classification. If you are in the blue part, it means that we have a good classification, and if you are in a green part, so the classification is perfect. As we can see here for our application, for this part, the classification is good. Also, we have another aspect, another metric that we can have a point of view about the performance of our model. As we can see here, for all of the surface with the risk of the squill, it can classify all of them, but it is just 5 surface that it's misclassified. So it means maybe the geometry is so near the geometry with the risk of vibration. Another thing that's so important in such an application, it's the aspects of multi-scale. For having a point of view about this multi-scale aspect, we did a test. At first, we did the training phase with the surface with the geometry so uniform without any little scale. After that, we tested with the little scale. As we can see, the ROC curve is not good. So the aspects of multi-scale can have a good or bad impact on our measurement. After that, we did the same thing with the little scale for training. After that, for testing with the largest scale. As we can see here, the ROC curve is more better. And here we have the visualization about the localization to the features for visualization, the feature sensitivity for having a point of view during the training phase or testing phase. Our algorithm is going to see which part of our surface. After doing that, for this classification, another thing is interesting. It was just looking at the surface geometry, can we have a prediction about the frequency of the vibration or not? Also, again, we are going to use a convolutional neural network because of the geometry of our surface for keeping the spatial form of geometry. Also for having more information during the training phase. As we can see here, it's the loss function. Just we had a little noise here, and after that, the model is stable. And about the results for this prediction of the frequency, the red circle are the predicted results, and the blue one are the real results. And as we can see for this part, also the model is good for this prediction. After that, we are going to have a point of a discussion about interaction between bodies and the evolution of the temperature. For this part, we use the test bench for having the experimental data. As we know, always it's not just the modelization data can be interesting for doing our deep learning application. After creating the data set, we are going to talk about the architecture of our AI model. After that, or about the interpretation of the results. As we can see here, for generating this data set, we used a bench test with this geometry. And the bench test was a pin on disk, exactly the same that we had for modelization in the previous chapter. After that, we put the thermocouple here for having more information after contact. Because when we have the contact, we cannot see, when we have two bodies in contact, we are not going to have more information during the contact process. For this reason, the evolution of temperature can be a good representative of the phenomena during the contact. We did it about 600 tests, and as we can see, the blue point are the test used during the training and validation, and the rest the points are the data for testing our model. The rotation speed was a feature during the test, the duration and the normal force for creating this data set. As I said, for having information during contact, we placed 8 thermocouple, but we lost 2 thermocouple during the test. And we continued the test using 6 thermocouple. As we can see here, our performance of the thermocouple and the evolution of the temperature is not linear. Also, during the time, it's not linear, and also for each thermocouple is not the same. So our problem is so complex. Like input for training and testing, training and validation, we would like to use just the evolution of temperature just in the start of the test as a noun. Also the normal force like noun, because it's us who apply the force during the contact. And the target is the prediction of the evolution of the temperature during the contact. We applied different strategies like recurrent neural network or LSTM. At first, here we applied the trend. We used the whole of each test like inputs, and when we test it, as we can see here, the prediction is so bad. The second strategy was testing the model, training the model from 0 to this red line, and after that to the prediction for the left of the evolution of the temperature. As we can see here, the prediction for this test is good, but when we apply on the other test, it's not good. The real test is that, but here the prediction is not so good. So we needed to find another idea for solving this problem. Another idea was this idea. This one, for this time, we are going to cut each test for 5 seconds, and the 100 for 5 seconds, and each second is 50 frame. So we are going to use 50 frame like input, and just the frame after the 50 frame like output. For doing the training phase. After that, we are going to use just the 5 second like input, and when we have the output is going to be like an input, and we are going to reconstruct all the tests using this idea. Here we have some results after applied this idea on this test. So we are going to have see here the evolution of the temperature for the prediction is not bad for all of the test. And when we are going to have another aspects of mechanics, it's this spectrogram, and we can see when this spectrogram is uniform, the prediction is good. We are going to discuss about the other test. Here we have a test just with a little different between the previous one. And as we can see, when we have a noisy spectrogram, the model cannot be more good. And another test, when we are going to have more evolutionary of temperature evolution, as we can see, the model is not also. And when we are going to talk, when we are going to look at the spectrogram, as we can see, when we have a spectrogram is so noisy, so the model is not going to have a good prediction. For this reason, we need to establish a meta model or to find what is the difference between this different spectrogram, different behavior of our system. The difference between all the tests is one just the normal force. So when we are going to change the normal force, the behavior of the system is going to change. The idea is for the AI model, if we change the force of this test with this test, what will be the results after this changing for our AI model? As we can see here, the red curves are the results of the AI model, and the blue one are the real results. So our model is going to say to us, if you change just the force, the evolution of the temperature on your surface is going to change. So here we need to have a criteria when the evolution of the surface, the temperature of the surface is going to change. What can be the effect on the surface, on the performance of the system? As we can see here, we are going to try to use this evolution and just analyzing the in terms of the frequency generating by the system. As we can see here, the input is just the temperature evolution, and as we can see, we can have a good prediction about the intensity of the frequency. But when we have the chaotic spectrogram, always we are not going to we are not good to do this prediction. So this time we are going to discuss about the evolutionary of aspect on the surface for having more information during the contact process. For doing that, we can discuss about this aspect in two aspects. The first one is the evolution of the surface. The other one is the mechanical fields. These mechanical fields can be generated using finite element methods. At first, we are going to talk about the evolution of the surface. And for this one, also, we are going to have this scenario. For creating the data set, we are going to use the same bench test. And after each breaking test, we are going to do a test. The test name is profilometry, for having more information about the evolution of the surface during the contact process. After that, finding a good architecture adapting to this problem. And at the last, we are going to talk about the results. For creating this data set, we use the same the bench test for the evolution of the temperature. And after each test, we use this instrument for doing the profilometry, for having more information about the surface geometry. The features are the normal force, or the duration, and the rotation speed for each test. We choose the supervised learning algorithm, and the algorithm was generative adversarial neural network in a short GAN. And as we can see here, it's the input, it's the expected output, like the real results, and it's our output from our deep learning. It's not good. So we needed to find another solution for having a good prediction. This time, using this method, we are going to increase our data set. We used this method for having subset of each images for increase our data set. And after that, we can see here, this is the this is the real, this is the input. This is the output of the real experimental test, and here we have our prediction. It's not so good, but it's more better than of our previous application. So for having more better results, we need to apply mechanical fields for adding to our surface evolution for having a good model. This time we are going to use the same model for generating the surface, but the output of this finite element method is the mechanical fields like the stress field. After creating this data set, we applied our model for doing the prediction about the mechanical fields. And as we can see, the input is there, the surface geometry, and here we have the real results, and here we have the prediction of our model. As we can see, it's not bad, and it's good to generate the mechanical fields using generative adversarial neural net. For having an overview, we talked about the contact and the braking systems. We talked about the multi-scale and multi-physical aspects, and also we talked about the coupling AI and mechanics, and the necessity of the considering the physics in our applications, or considering the evolution of the surface, temperatures, all of them. For the perspective, we are going to work about the generative the spectrogram using GANs, and here you can see such results. And this works are going to with Bowman, and he's going to defend his thesis next day. Thank you for your attention. If you have any question. Thank you. So, as I was, seeing multiple approaches for this aspect of this race, like the sort of this rate. And at the end of this room, maybe I'm yes, but the information. Do you have any perspective to try to combine this information to try to find the optimal parameter to start with? Yeah, of course. That's a thesis. It was a thesis after my thesis, and also there's another thesis is always to do. But the person after me is going to consider all of these aspects for having a general model. For now, I changed a little my search fields, but always in contact with our colleagues in the university. But for the other person, it's not working. So, thank you.
Thank you for your presentation. I was wondering more from everything. So I know one of the issues change database station. I was wondering same image.
That's right. If you change the range or if you change the material also, we are going to have another performance, another behavior. For this reason, I would like to work about not just physical informal network, and also work about how we can have more information and how for have more information at first, and also for adding more instrument for having multi aspect data for increasing our performance at first, and have a model with possibility of the general model. So I mean, we change one of the parameter, the model can change the performance.
That's a very difficult question. It's like very simple one for you, I guess. Just 35. When you do the database, yeah. Is there a reason why you are sampling random things? I choose from map instead of getting it in rows and rows.
Yeah, because when I use this technique randomly, I could to have more detailed window. But if it's just cutting, it's just the same pixels or the other test. But using that, when I have the slide window, the step was just about why this file can help for having more data. But just cutting is very
so you are sampling a lot actually. You're sampling a lot of things.
Yeah.
Much more than if you were
just exactly. Yeah.
Which response. So basically, so you said that you are using the model for generating data. Are you really controlling?
Yeah. We can.
How does it work?
We can change the altitude of the each point randomly, and each time that we have the here I think it was and when we change the altitude of the points, the performance of the model and the behavior is changed.
So you are controlling at
It was just like a matrix, and in this matrix, x and y are constant, and just the z is changed for generating the data.
This is realistic. I mean, it's
it was
correlated with what you're observing.
Yeah, it was a thesis of Yassin Wadat, the thesis P41 thesis. It works in the context.
Another question from this part. So our AI models seem to work pretty well. And but my question is, does it make sense to transform this program into binary form? Are you? I was wondering if you rational.
Yeah.
That was
Here, at first, we had a binary classification for the surface with the risk of spinning or not. And after that, using the same surface, we used the model for regression. For having a regression, this surface can generate which frequency at which time.
Again, premise himself because there are only a few false positives. So I was wondering if you analyzed those counter examples to see what are the peculiarities of these services that yeah, led to yeah,
For this reason, I would like to show these results that we have here. We understood that the points that are in these zones are more important. So we had 5 surfaces misclassified, and these this 5 case misclassified was more similar of the other case. So we needed to just using another type of analysis like p-value for having more information, for having more uh, sensitivity about our model. For example, our model is sensitive in the image parts, but the parts are more important for this problem are there. And for this 5 case, we had a lot of similar in these zones.